So hello everyone, my name is Preet Savalia and today I am excited to present our paper NGD, Neural Gradient-based Deformation for Monocular Garment Reconstruction. This work tackles the challenge of creating dynamic 3D models of clothing using only a single video camera. So what is the core problem? It's monocular garment reconstruction. Our goal is to take a simple 2D video of a person, like one from a phone, and from that generate a complete high fidelity 3D model of their clothing. This isn't just a static model, it's a dynamic one that moves, folds, and wrinkles just like the real garment frame by frame. This is incredibly difficult because we have to infer 3D shape, complex motion, and fine details all from a flat 2D input. We are solving a massive amount of missing information. To understand our solution, we first need to look at the engine that powers it, gradient-based deformation. The question is, how do we programmatically deform a 3D mesh? Instead of just moving vertices, which is a chaotic, a more robust way is to define our target deformation on the surface itself. We do this by defining a deformation Jacobian for each triangle face. This frames the problem as a discrete energy minimization. We want to find the mesh vertex positions that best fit our target Jacobians. The optimal solution to this can be found by solving a large sparse linear system, a Poisson solve. The key takeaway is that this entire operation is differentiable. And as your slides notes, because the math is well structured, we can pre-compute many of the operators and solve this extremely fast using a Cholesky decomposition. This gives us a fast differentiable way to deform a mesh, which will be the core of our geometry module. So here is the high level overview of our method, NGD. It's composed of two main modules that run in parallel, a geometry reconstruction module and an appearance reconstruction module. The geometry module is our workhorse. It takes the video frames and body pose, and its job is to output a detailed posed 3D garment mesh for every single frame. At the same time, the appearance module learns the texture of the garment, not just its flat color, but also how it interacts with light and shadow as it moves. Both of these modules follow the same core philosophy, decomposition. We split the problem into static frame invariant component and a dynamic per frame component. This decomposition is the key insight of our paper. Let's dive into the geometry module. As I said, we decompose the problem. We define the final deformation Jacobian for a frame T as the sum of two separate fields. First, a static Jacobian field. This is a single field that is optimized across all frames. Its job is to learn the garment's fundamental unchanging shape, its canonical design, like a collar, seams, or a specific cut. Second, a dynamic Jacobian field. This field is a per frame component and it's predicted by a neural network. We condition this network on the body pose and mesh normals. This network's only job is to predict the local non-rigid changes, the wrinkles and folds caused by body's movement. So the static field learns the garment and the dynamic field learns the wrinkles. We add them together and solve the Poisson system to get our final detailed canonical mesh. This mesh is then put into the correct pose using a standard skinning transformation, and we compare it to the video to calculate our loss. But this system has a problem. What if a sharp wrinkle forms in the middle of a large flat polygon? Our mesh doesn't have the resolution to model it. To solve this, we introduce our gradient-based adaptive remeshing strategy. This is a novel idea that lets the loss itself guide the refinement. So here is how it works. We calculate our rendering loss, L diffuse. We backpropagate the image space gradients of this loss all the way back to the mesh faces. This gives us an error map on our 3D model. We can now see which faces are causing the most error. We then select the faces with the highest gradients and perform edge splitting on them, adding new vertices. This is incredibly powerful. It means we adaptively add detail only where the model is failing, allowing us to capture high frequency wrinkles without the cost of a uniformly dense mesh. For the appearance module, we use the exact same decomposition philosophy. The final texture is the sum of two texture. A static texture, this is a single high resolution texture map that learns the garment's base pattern or color. It's optimized across all frames. Second, a dynamic texture. This is a low resolution map predicted by a small neural network. It's conditioned on the pose and UV coordinates, and its job is to learn the per frame lighting and shadow effects that are cast onto the garment as it folds. This decomposition is crucial. It prevents the network from baking a temporary shadow into the permanent texture, which is a classical problem in this field. We benchmarked NGD against several state-of-the-art methods on standard datasets. As you can see in the table, our method significantly outperforms all of them. We achieved 33.6% improvement in chamfer distance, which means the geometric accuracy of the mesh, and 2.4% improvement in normal consistency, which means our surface details like wrinkles and are more accurate. These numbers confirm that our new contributions, the decomposed fields and the adaptive remeshing, are highly effective. The numbers are great, but visible results are even clearer. Here you can see our reconstruction compared to the prior work. The other methods tend to produce blobby or over smooth results. They capture low frequency motion but completely miss the finer details. Our method on the right is able to on the bottom is able to reconstruct sharp, plausible, high frequency wrinkles and folds. The difference is fidelity, especially on the loose garments. So this is where our method truly shines. Here you can see our final generated 3D model in the action. On the left is the ground truth, and on the right is our reconstruction. Notice how the fabric realistically moves and deforms in response to the body's motion. Our model captures not just a large-scale movement, but the subtle secondary movement of the fabric. The wrinkles form, travel, and dissolve, and our dynamic texture map correctly adds shading to those folds, all generated from that single 2D video. Here you can see the texture. To validate our design choices, we ran several ablation studies. First, we tested our main rendering loss. We used a diffuse loss which combines UVer and SSIM loss. We compared this to the more common normal map supervision. The results are clear. The normal based supervision is very noisy and fails to find a good solution. It gets stuck in a local band minimum. Our diffuse loss is much more robust and provides a smoother gradient, guiding the model to a far more accurate and stable reconstruction. Next, we wanted to prove the value of our adaptive remeshing module. On the top, you see our full method, and on the bottom, you see exactly that without the remeshing step. The difference is night and day. Without remeshing, the model is blurry and over smooth. It simply does not have the vertex resolution to represent the wrinkles. With our gradient-based remeshing enabled, the model intelligibly adds details, resulting in the sharp, high-frequency reconstruction, as you can see on the top. Finally, we found that optimization could sometimes be unstable and get stuck. We introduced a simple but powerful heuristic, adding exponentially decaying noise to the mesh vertices during the initial stages of the training. As you can see, without the noise, the model can overfit to local details and get stuck, resulting in a noisy and incorrect shape. With the noise, the model is shaken out of this bad local minima, allowing it to find the correct global shape first before settling into the fine-tuned details. This simple trick made our optimization more robust. So to conclude, we have presented NGD, a novel system for monocular garment reconstruction. Our key contributions are a decomposed neural Jacobian field that separates the static garment shape from dynamic per frame wrinkles, a novel gradient-based adaptive remeshing strategy that uses the loss itself to guide mesh refinement, add a parallel decomposed appearance module that separates base texture from dynamic lighting. Together, this allows our method to achieve a state-of-the-art results, generating high-fidelity, dynamic 3D garments from a single 2D video. Thank you.